All right, everybody. We are starting on time today. So I'd like to welcome you to our today's webinar. My name is Andreas Lotz, and I'm working for Anton Power as a product manager responsible for our smart pave DSRs, as well as for our quality control view meters, the MCR 72 and 92. Today, I would like to explain two elementary methods for asphalt binder testing, which are the methods AASHTO T315 or ASTM D7175, as well as the AASHTO T350 or ASTM 7405. Prior to this, I would like to explain really quick some basics of rheology, as well as the devices Anton is offering for all kind of rheological tests on asphalt binders. If anybody want to learn more about the basics of rotational and oscillatory rheological measurements or methods, I can strongly recommend the webinar of my colleagues, Mr. Thomas Metzger and Mr. Christopher Giel on the 9th and the 10th of June. So today we only will learn really the basics we need for the asphalt binder test methods. So let's start. So what does rheology mean? It is describing the deformation and flow behavior of all types of materials like water, oil, or viscoelastic materials like shampoo or ketchup. The term rheometry is describing the measurement of rheological data, for example, under the use of rheometers or DSRs, dynamic shear rheometers, which can be used to determine the full sample behavior, also, for example, at different temperatures or other climate conditions. So at Anton Power, we are using the so-called road of rheology to describe the behavior of different materials. On the left side of our road, we can find ideal viscous materials, like I already mentioned. These are oil or water, for example. These materials are showing most likely ideal Newtonian or ideal viscous behavior. On the right side, we can see materials like steel or stone. For example, these materials are called ideal elastic materials. In between, we can find anything else, like paints or coatings. These materials are often viscoelastic liquids. Other samples we can find as viscoelastic solids are, for example, rubber or pastes. So our bitumen, of course, can be found all along this road. For example, a unmodified binder, we are measuring at higher temperatures, is showing a nearly ideal viscous behavior, while it is showing the ideal elastic behavior if we are cooling it down to negative temperatures, and then it is becoming more and more brittle. Sorry. So to explain how we get the values we need for the asphalt binder test with the rheometer, the so-called two-blade model can be used to explain the way how the basic values are calculated. So we can imagine that the lower blade is fixed and the upper blade is rotating and is shearing our sample. Unit shear stress, just tau, is the force which is needed to move our sample over a defined area. The unit for tau is Pascal. The shear rate, gamma dot, is the velocity over the height of the gap, and the unit here is 1 divided by seconds, or called reciprocal seconds. So this is a rotational test, and for good rheological values, we must be sure that we are having constant flow between the different layers and also between our whole blades. If, for example, the gap is too high, we cannot be sure that the whole material within the gap is sheared. Furthermore, we could have the problem that the material starts to flow out the gap, which would lead into lower values than we expect. This is especially a problem if you are measuring at higher temperatures, where our material becomes more liquid. On the other hand, the gap should not be too small, especially if we are measuring samples which include particles like binder mastics. Luckily, in the case we are measuring according to AASHTO T315, for example, the gap for each measuring system is predefined in these standards. So out of the values we are already get, we can calculate out of tau and gamma dot the rotational viscosity eta. And the unit for eta is Pascal seconds. Previously, there was an old unit which was called centipoise. However, we do not use this unit any longer because it is not an SE unit. So how is viscoelasticity measured? We are using oscillatory measurements for this, where the upper plate is not rotating, but oscillating around a fixed point. The oscillations are applied in a sinusoidal manner, where the oscillations are that small that in the ideal case, the inner structure of the sample is not changing. Under the use of a so-called amplitude sweep, where we are keeping the frequency constant and increasing the amplitude during the test, we can analyze how much force or how much torque we can apply to the sample without changing the inner structure. There we are talking about the linear viscoelastic range, and this is the range which we are, by doing this, we can figure out the maximum force we can apply to the sample until it starts to break down. So this is also again our two-blade model and our sinusoidal wave. So what we are doing is the amplitude in this case is the height of the peaks, while the frequency is the time which the system needs to perform one full cycle from here to here. The set wave, the preset wave we are sending starts at 0 degree, and we are getting an answer which is shifted in some way. So based on these two curves, we can calculate the phase shift angle delta, which is representing the viscoelastic behavior of our material. So this is a very illustrative example to see how the phase angle from the oscillation experiment is evaluated. Here we can see how the sample is behaving within the gap. So we are presetting a value, in this case, the amplitude and the frequency, which is here represented under the use of the green dot. But this is our upper plate, which is moving. And we are getting the blue point here as an answer. So depending on the sample, we are getting an answer in form of the phase angle. If the phase angle is 90 degrees, the sample is an ideal elastic liquid, like we can see it on the left hand. If the phase angle is 0 degrees, like we can see it on the right hand, the sample answer is in line with the preset value, and we are having an ideal elastic solid. In between, we can find again our viscoelastic liquids. This is the case if the phase angle is larger than 45 degrees, or our viscoelastic solid, which is the case if our phase angle is smaller than 45 degree, which we can see here. It's also nice to see here that all the layers are showing a good, or are showing a constant behavior, constant flow behavior. So the phase angle delta always lie between 0 degree and 90 degree. And viscoelastic materials have phase angles which are larger than 90, which are larger than 0 degree, but smaller than 90 degree. Our asphalt binder or our bitumen with approaching 0, very approaching 0 degree, usually are too solid at a measured temperature and can have problems with cracking. But these binders are usually having, again, a good resistance against rotting. Binders approaching 90 degree phase angle usually are to a liquid at a measured temperature and may have a good crack resistance, but problems with rotting because this kind of binders are too soft. So again, we are having our example of 0 degree phase angle, which is steel, or in this case, oil for 90 degree phase angle as an ideal viscous material. Another important value for the bitumen industry and for our standards is the complex shear modulus G star. This value is representing the stiffness of a sample. In this example, we are controlling the strain and we are getting the stress as an answer. So G star is in this case calculated from tau divided by gamma. And to achieve the set displacement, the strain, a certain amount of torque, which is the stress, is needed. If a higher torque is needed to achieve the given strain, the sample has a larger value for G star. So now we get the really basics of our values. Again, there are especially basic of rheology seminars held by colleagues of mine. And now I want to talk a little about the general rheological behavior of different bitumen samples. As all of you know, bitumen is showing a really strong temperature dependence. So it is really softened and liquid when we heat it up, and it is hard and becomes more and more brittle when we cooling the material down. In this example, in this diagram, we put together so-called temperature sweeps where the deformation and the frequency were kept constant, but the temperature changed. So the blue curve is an unmodified binder, and as we can see, it is the softest of these 3 samples, which we can see on the G star value. Furthermore, the blue sample becomes nearly ideal viscous at around 70 degree, because here the phase angle is quite close to 90 degree and even becomes 90 degree at a little higher temperatures. The other extreme here is the green curve, which includes a high amount of modification. So the green curve is showing the highest stiffness, which you can see here on the G star value. And it is now becoming ideal viscous. It is more like behaving like a viscoelastic liquid in the range from 70 to 40 and behaving like a viscoelastic solid in the range from 40 to 10 degrees C. The red curve is somewhere in between. The interesting thing here is that at the highest temperature, it is also becoming nearly ideal viscous, but we are having a plateau in the range from 30 to 60 degrees C in the phase angle, which means the viscoelastic behavior in this range is not changing that much. So this diagram is showing the Newtonian behavior of an unmodified asphalt binder at 160 degrees C, measured under the use of a cylindrical system. In the beginning, we can see that the viscosity is dropping down a little, but at a shear rate of approximately 100 reciprocal seconds, the viscosity gets constant. In this example, the shear rate was held constant at 1000 reciprocal seconds, and due to maybe shear heating effects, we can see that the viscosity dropped down a little more. And this is a good example of a nearly ideal viscous material, since if we are lowering the shear rate from 1000 back to 0, the viscosity even then is not changing that much. So next I want to talk about the devices, the dynamic shear rheometers ANTOM-PAR is offering for bitumen testing. We are having the SmartPave 1 or 2, which is our device or the choice for asphalt testing labs and also research and development. So with this device, nearly all kind of tests can be done. Also measurement of solids like cylindrical samples under the use of the oven. The other device we are offering is the SmartPave 92, which is developed especially for the daily quality control and routine measurements in asphalt labs. So both devices are using the high dynamic EC motor and coming with a air bearing of high stiffness. The 102 is having a wider torque range than the 92, and it is also coming with normal force control. Both are using the same software, Real Compass, which is including templates for all international standard methods like AASHTO, ASTM, EN, ISO, or GHOST standards. And even if you should not find a method, our support team will create and send you the needed template. Furthermore, it's also possible with the software to create your own templates or to adapt existing methods from scratch. Depending on the accessories, we are having different temperature range. The standard temperature range of a SmartPave 1 or 2 is -30 to 120 degrees C. However, under the use of a HPDD 200, we can increase the range from -40 up to 200 degrees C. And with special measuring systems, we are able to keep the gradient much smaller than 0.1 degrees Celsius. Furthermore, the accessories are heated under the use of Peltier's elements, so we can heat and cool with these elements. And a combination of radiation and conductive heating is used. For the MCR or the SmartPave 92, there's even no need to have a counter-cooling bath because it is cooled. The Peltier's elements there are cooled down under the use of vents. The other big advantage of the SmartPave series is the automatic temperature calibration, which is eliminating the temperature offset between the rheometer temperature sensor and the sample area between the blades. We are using an external GMA 3750 thermometer and a calibration sensor, which is traceable. And also there's a gap setting profile available, which is keeping the sensor in place during the whole calibration process. Here you can see the calibration procedure in the software. The only thing you as customer must do is connect the sensor and the thermometer to the device and type in the temperatures you want to have calibrated in this line and press start. And the rest is done completely automatic by the device and the software. After the calibration is done, the protocol of the calibration is stored in the software and can print it out or present it as a PDF at any time. This is a list of the standard methods fulfilled by the devices. As you can see, the SmartPave 1 or 2 is fulfilling all international standards. It's coming with master curve analysis, and depending on the accessories, you can do more tests. So finally, I'd like to start with the method T315 or ASTM D7175. The superpave system, which is the background of this, was a result of the first strategic high-ray research program as a part of the performance grade system. The rheological value G star and sinus delta were implemented. So these properties relate to the rutting or fatigue cracking failure models, and the PG system is based on the idea of using binders that suit the climate conditions in which they are used at high and intermediate temperatures. Therefore, temperature measurements were performed all over the US and Canada, and the values were measured within the surface area of the road. So there is an actual sensor in the road, and the temperature is measured there. As an example, we can see here a PG 76 minus 22. The high PG value, 76 degree, is the average of the maximum pavement temperature from 7 consecutive days. And the low PG in this example is minus 22 degree, which is the minimum pavement temperature within 1 year. In the United States and Canada, there are more than 7,900 weather stations observing the temperature of the areas. So based on these values, the decision can be made which binder should be used for which region to ensure a long durability of the road. So the test requirements of AASHTO T315 are also valid for other AASHTO methods like AASHTO T350, the MSCR test, and which is also following these requirements. We're having different blades depending on the aging level of the binder, 8 millimeter or 25 millimeter. We are having an environmental chamber which must enclose a temperature control within the specimen of 0.1 degrees C. The controller must be also able to control temperatures from 3 to 88 degrees C with accuracy of 0.1 degree, and an internal temperature detector mounted within the environmental chamber close to the fixed blade also must have the resolution of 0.1 degrees C. And the loading device must provide stress or strain controlled sinusoidal oscillatory load with accuracy. Of course, with modern rheometers, it is not a problem at all to meet all of these requirements. The measurement for grading and verification is more or less identical. And the deformation value is depending of the aging of the material we want to measure for original and RTFOH binder, which is simulating the aging while the material is mixed and installed, is the frequency constant for all types of measuring with 10 rad per second. And the strain we are using is between 12% strain for original binder and 10% for RTFOH binder. So original and RTFO binder is used to determine the high PG value, and PAV binder is used to find the low PG values. This value consists also of the results coming from the bending beam rheometer. So we need an additional device to get the low PG value. However, for original RTFO, a 25 millimeter plate with 1 millimeter gap is used. And for a PAVH material, an 8 millimeter plate with 2 millimeter gap is used. The result criteria is also depending on the aging. It is between 1 kilopascal and 2.2 kilopascal for original RTFO and G star multiplied sinus delta must be smaller or equal than 5 megapascal for PAV residues. Again, we are setting the strain and the displacement, or the displacement of the sample, and as an answer, we are getting the values G star, which is our stiffness, and the sinus delta for viscoelastic balance. For the grading of an unknown original or RTFOH binder, the procedure starts at a low temperature, which should pass. In this example, we choose 64 degrees C. Then the temperature is increased by 6 degrees, and the test will perform again after the temperature was kept constant for 10 minutes. So this procedure repeats until the criteria, the fail criteria is reached, in this example, 2.2 kilopascal. And we can see that this binder is failing at 82 degrees C. For grading testing, the test temperature is varied to determine between which two temperatures the sample moves from pass to fail or vice versa. And the pass-fail temperature is calculated. So this is done automatically by the software. For PVH binders, we are lowering the temperatures in 3 degree steps, so we do not increase like for original and RTFO, but we are lowering the temperature now in 3 degree steps. And we are doing this until we are reaching the fail criteria, which is larger or equal than 5,000 megapascal for the verification. Usually the grading is performed by the bitumen producers, and final customers are only performing the verification. So at the data analysis is working as follows. We are conducting 20 cycles of data, but only the last 10 measuring points are used to get the results. So the first 10 points are to ensure a homogeneous sample behavior. And if the average value meets the criteria, the measured sample passes for that temperature. So far, that's for the grading method. For AASHTO T350 or ASTM E7405, which is the characterizing on high temperature performance properties, we are using the so-called MSCR test, which means multiple stress, creep, and recovery test. So since the SuperPave system was based on unmodified binders, and the usage of modified binders during the last years increased a lot, a new method for polymer modified material was necessary because these two sorts of material are behaving differently. And furthermore, the PG grading is blind to modification and is not correlating with the rutting behavior of asphalt binders. So the multiple stress, creep, and recovery test was developed as a performance-based test, which relates to the rutting potential of modified asphalt binder. You can here see in these two examples. In the upper picture, we're having a PG64 minus 22 modified, and it's not showing any rutting. And at the lower picture, we can see a PG67 minus 22, which is a unmodified binder, and we are seeing a 50 millimeter rutting here. Okay, to be honest, from this point of view, it is quite easy to say there is no rutting, but we just trust that the picture is right. So polymer modified binders are often or usually include polymer chains, and other connections which are usually not breaking down, and also they should not break while we are testing it according to AASHTO T315. And also the grading does not describe the material behavior under use conditions. So this is why the MSCL test was invented. This test is giving us the possibility to check how much the inner structure is recovering after a certain amount of force applied. So based on this, an estimation of the rutting behavior can be made by measuring this binder. So while AASHTO T315 is a oscillatory test, AASHTO T350, the MSCR test, is a rotational test. But again, can be all used under the use of the same device. So general creep and recovery test can be seen here. We are setting a stress in tau in this case, and for a certain time. And directly after we applied this force, we are measuring the recovery of the sample, and we are applying no force at all in this step. So between T0 and T2, which is the creep interval, and between T2 and T4 is our recovery step. So this is a single cycle, the same as we are using it at the MSCR test. The applied shear stress is removed in this part, and we are measuring the recoil of this sample via the deformation of this interval. So the multiple stress and recovery test is performed at the high PG temperature on RTFOH materials, and the control and measured parameters are here the applied stress, which is the force we need to deform the sample, and the resulting strain. And we are applying a stress of 0.1 kilopascal for 1 second, directly followed by a recovery step where no force is applied. So this is giving us the possibility to measure the relaxation of the material for 0.1 kilopascal. 20 cycles are applied, but again, only the last 10 cycles are used for calculation. And the first 10 cycles are to ensure a homogeneous sample behavior. Directly after this, we applied stress is increased to 3.2 kilopascal. And same here is 1 second loads and 9 second recovery. But now we are using all steps for the calculation of the results. As an output, the software is calculating the percent recovery, which is showing how the sample returned to its previous shape after a load was applied. It is the difference between the strain at the end of the recovery period and the peak strain at the end of the creep period relative to the peak strain, which you can see here. Also, we are getting a value for the non-recoverable compliance, which is the unrecovered strain, which we can see here. And the stress sensitivity parameters JNR difference, which is the difference between JNR level at 3.2 kilopascal and 0.1 kilopascal. And this value must be equal or smaller than 75%. So MSCR results according to AASHTO M332. We are getting the percent recovery, which is plotted versus the JNR value. And the boundaries we are seeing here are established based on the measurement values at 3.2 kilopascal. Here, a simple above the line, below the line pass-fail criteria is used to ensure there is suitable amount of modification in here. So above the line, it's indicating that the binder is modified with acceptable polymer amount, and below the line, the binder is not modified with any elastomer. So usually, if there is no modification at all, we even would not measure any recovery, because unmodified binders at high temperatures are not showing any recovery. They're behaving really often more or less like ideal or viscous materials. To summarize, the MSCR test allows a better verification of high temperature related properties of RTFOH and polymer modified binders at the climatic conditions for the road location. So it eliminates the PG Plus test, which was designed to create the elastic response of binders, and it is providing us two parameters: the shear sensitivity parameter, which pinpoints binders that have a high chance of performing poorly at high stress levels, and the percent recovery of the percent recovery versus the JNR, which is our non-recoverable compliance, which pinpoints binders which have effective elastomeric modification to migrate rotting. And also the JNR value is correlating to the rot depth according to test tracks on field studies in laboratory tests. So this was a quick overview about the needed basics of rheology, as well as an overview about the two most important standard methods. And thank you for attending our today's webinar. And if you are having any questions, please feel free to unmute you or ask or type your questions in the chat. Of course, you can also send me an email to andreaslutz@antonpar.com. Yeah. So there's a question. Can you explain again the difference between modified and unmodified binder, and how these two samples will show different results using the given templates? Yes. So a modified binder is a binder which is modified under the use of different polymers, or the reusage of shingles or old asphalt binder. And the difference in the results is for the MSCR test. A modified binder is showing recovery usually at all steps, while a unmodified binder is not showing any recovery. So this could also, in an extreme case, this could lead into negative values for the MSCR test, which is honestly just a physics. So if you imagine you're having a cup of coffee and you are pouring some milk in it, and you stir it with the spoon and you stop the spoon, the material is still flowing because the applied force is high enough to keep the material flow. And this is just the physics behind it. This is the reason why we are getting negative, or why it can be happening that we are getting negative values if we are measuring a unmodified binder under the use of the MSCR test, because often these materials are showing ideal viscous behavior at these high temperatures we are measured in. There's also a question why in some cases we check G star divided by sin delta, and in PAV G star modified by sinus delta. This is because the G star divided by sinus delta is the value we need for the high PG value, for example, 64 degree, and the delta multiplied by G star for the PAV is needed to get the low temperature grade, and therefore it is also a second test needed where we are using the bending beam rheometer. So also we cannot increase or we cannot measure materials like PAV H binder under the use of a 25 millimeter blade, because the force we need to apply to make this material move according to the standard is usually not high enough to make this material move under the use of a 25 millimeter blade. So the torque, it's easier to apply the torque to stiff samples under the use of smaller blades. This is, for example, also the reason why the so-called low temperature method is using a 4 millimeter blade. This method is used to determine really low temperature behaviors. And why PG increases 6 by 6 degrees C? So this is honestly a question I cannot answer. So it's defined by the standard. So sorry for this. So, okay, I just want to type in my email address to the chat. And if you're having any questions, please feel free to send me an email. All right, if there are no other questions, thank you again. Stay safe and have a good day. Thank you.